Welcome back. Today we're going to talk about system ID. We're going to run through quite a few examples. I'll look at some first order systems, second order systems with real poles, complex poles at a couple different levels of damping ratio. So we'll go through step response, Bode response, basically beat this thing into the ground with examples. So we'll start out here with just a simple first order system here. I've created Bode plots and step response plots for all of these, and for reference I threw in the actual transfer function I used to create these just so we can see what kind of results we get. Now I will point out, so the first thing we want to do in a first order system is we have two things to find. We have the gain, which in this case is just 1, and it is in all these cases. But we can see that easily because at low frequency we got a 0 dB magnitude, which is 1 in just magnitude, and our step response with the step input goes to 1. So that gives us our our gain of K, or K is our gain, which is K, is equal to 1. I can look at the step response and I say that one time constant, tau, is going to get me to 63.2%. That's about there, and that's at tau equals 5. That worked out pretty straightforward. I can also take the Bode plot, and if I do my straight line approximation, since that part is right there at 0, I get, well, I don't quite get to, this is 1 over tau, right? So I get, I should get 20 in terms of my frequency, my break frequency. Doesn't look like I quite got 20. That's 20 there, so that's reasonably close. And if you just had real data, it'd probably get you a reasonable model. We can also look at where the phase crosses 45, because basically our angle of J omega, where omega is equal to 1 over tau in radians per second, is just going to be basically minus pi over 4. So that's 45 degrees, and I look at the 45, and that does cross right there at 5. And I'll also note that this, it's hard to see, should be about a 3 dB difference between the straight line approximation and the actual corner. Now here what I have is a system. It's a second order system. There's 2 real poles. There's a pole out here at minus 186, a pole at minus 13. My zeta, or damping ratio, is 2 in this case, so it's well over damped. Now what's going to happen is this smaller pole here, smaller magnitude pole, has the highest time constant, if you would, so the one closest to the origin is going to dominate. And if we were to, let's see, 1 over 186 is 0.0054, and 1 over the 13 is 0.0746, to give you an idea of about how long those are going to be around. 0.07, somewhere in here, that's right there. That's not that far from a time constant of a first order system, and this almost looks like a first order system, okay, because that one slow pole really dominates. If you look closely here, you can see that it's got this starting out like that kind of shape. That kind of gives you a little hint that there's something going on there, but that's hard to spot. So wouldn't be hard to assume that this is a first order circuit system, you know, with a time constant of something right in there, you know. And you wouldn't be that far off in terms of the behavior because those poles are fairly far apart. But we can see, if we look in the frequency response, that we have 180 degrees of phase. So that tells us there's two poles. I don't see any peak or anything. Now we can look at the phase going through 45 right there. And then the phase going through 270. You know, but the problem is these phases are kind of overlapping a little bit. Though it looks kind of, doesn't look bad from location of my first pole, but let's draw some straight lines. There's that. This is really harder to guess. Well, let me extend this up to, you know, if we'd made the mistake of assuming that this was a first order system and just tried to do a straight line and come up here, well, first our slope here is 40 dB per decade, not 20, so that should have been a clue. And this is obviously much more than 3 dB, closer to 6, which or 8. But so that's, you know, we know there's something going on there, and I can draw the second line, something like this, and I get a pole somewhere around 10 to the first. If I look at this closely, it's probably a little bit greater than 10 to the first. That's not far from this 13, and I've got a pole somewhere in here, which is 100. Well, I put my mark just above 200 when actually it's 186. But in practical purposes, you're probably going to be pretty close like that for a lot of applications. Okay? So, let's move on. Let's reduce our damping to 1. And now I have two real poles. Oh, the magnitude, again, K equals 1, because my step response went to 1, and this omega 0 is equal 0. So I got K, I've got in the location of two real poles. I don't need to calculate a zeta here because it's over damped, and I can just treat this as, you know, since I have two real poles, I can just treat it as two first order systems when I take the roots of that. So it would be like, you know, 2500 over S minus 13.4, or S plus, I'm sorry, S plus 186.6. So I could treat it just like that as two first order poles. So here I've got two poles. They sit right on top of each other. Again, the step response almost looks first order-ish, but you're seeing, you know, a real first order would have gone up like that, and you're seeing this hooky thing shape down in the bottom here. So that's something's weird. If I tried to do my 63%, I'd come up with about 0.04. You know, that's not really where the poles are at. Yeah, 1 over 50 is 0.02. So the, you know, my time, if each pole has a time constant, that's somewhere down here, not up there. So we got to be careful that we don't try to model this as a first order system with twice the time constant. And again, looking at our Bode diagram, I see 180 degrees of phase. I look at my magnitude and I see, golly, that's just basically a straight line all the way up. So that tells me those poles have to be really close together. This should be 6 dB, and it looks like it's not far off. If I look where this crosses 90 down here in the phase, somewhere thereabouts. Oops. That's not far off from where I crossed that 0 point, and that's right at 20, 30, 40, no, that's at 50. So that's right where our poles are located. So we found the poles in the right place. They're both real. So that would be our model of basically in k equals 1, and our poles are at minus 50. So that identifies pretty good. And it helps that I just use MATLAB to generate these and not real data. Here I've got a system with a damping ratio of 0.5. Now my poles are complex conjugate pairs. And if I look at let's go look at the step response first. If I look at the step response, I see that I have an overshoot. So that overshoot tells me that I have at least the second order system. So what I'm going to look at is I'm going to find omega n and stuff in my omega d. Omega d is kind of tough. I don't have a lot of oscillation. I could look at the time from here to here and say that omega d equals 2 pi over t d. That's a pi. Equals omega n times 1 minus zeta squared. Then I have to find zeta. That gives me, basically, if I look at those times, I've got 0.15 minus 0.075, and that gives me 0.075. But that's only a half cycle. And actually, I should have been over here. I was drawing very carefully. So that's times 2 and gives me a omega d equal to 42 radians per second. And that's, the damped ratio or damped frequency is going to be slightly slower than the natural frequency. So 42 seems reasonable for a damped frequency. But now I got to find zeta to put into this calculation here. I can't really use the log decrement method because I don't get, a couple cycles. I don't get good cycles here to do that decrementing over. What I really need to resort to here is the percent overshoot, because I have a good overshoot there and I can work with that. And my overshoot here is equal to 0.16. And I know that the zeta over the square root of 1 minus zeta equals 1 over pi omega n times yf minus yo. That's the final versus the initial over the overshoot. Now in this case, yf equals 1 because it finished out at 1. Y0 equals 0. We started at 0. Our overshoot is at 0.16. I can chug this all through and I get if I solve this equation for zeta, no, I'm not going to write it out here. I'll let you see that. So I end up with a zeta equals 0.504, which is pretty darn good. I'll write it out. I'll write out the equation. Just since I have the numbers already done, I can erase those. And so if I take this equation and I can solve that, and I get zeta equals 1 over pi times the log of yf minus y0 over os divided by square root of 1 plus 1 over pi log of the yf minus y0 over overshoot squared. And, you know, it's messy, but it works out. And I can't really use the small zeta approximation. If we were to use the small zeta approximation, it says basically we ignore this 1 minus zeta. Yeah, I thought that was wrong. Okay, I'm sorry. That's the 1 minus zeta squared. So, and all those other things, that was a zeta squared. Sorry for the dead air space there. If I use the small zeta approximation, I assume that 1 minus zeta squared is equal to 1 when I take the square root of 1 minus zeta squared. I would say that zeta equals 1 over pi log of yf minus y0 over overshoot. And that would lead me to 0.18, which is not that close. So when I've got fairly high damping where I just get an overshoot and settling, I really can't use that small zeta approximation. So I got to go through all the math to solve this equation for zeta and all that entails, okay? But I came up with the right answer doing that way, which is always nice. And then I can say my omega n equals omega d over square root of 1 minus zeta squared. My omega d was equal to 42, if you recall. And I come up with an omega n equals 48.6, which is pretty close to the 50 that I used when I created this data. So that was the overshoot. I can't use the log decrement or anything like that because there just isn't oscillation. But we can go back and look at our Bode plot, and I get a little bit of a peak there. Okay, it's not much. I've blown it up over here on the right, so you can see you've got a peak right in there, but even that isn't a lot to work with. I think the best solution for finding the zeta in this one, and finding omega n and zeta actually, if I look for where it crosses 90 degrees, I get basically 5 radians per second as my omega n. And I can look at it in this blown up one here, that's right there. So that gives me an omega n 50. My k, again, it's 0 dB, so k is equal to 1. And for the phase, I can use the slope method. But to use the slope method, I can't do that directly from the Bode plot because I need a linear plot of frequency in radians per second, and linear, and phase in radians, not in degrees. The Bode plot tends to be in degrees. So I got to make a whole new plot. I look for the phase to cross pi over 2, which is 1.57, somewhere right in there. And again, that happens at that 50 radians per second. And I can say that zeta equals minus 1 over omega n times d phase by d omega evaluated at omega equal omega n, and the inverse of that. So it's really the change in omega with change in phase. But when I draw a straight line through there, as best I can, and pick out some points, I come up with a delta phase points. I did this a little bit earlier, of minus 1.2 to minus 1.9 gives me a delta phase of minus 0.7. My delta omega is equal to, at those points, was equal to 41 and 59, and I should have written them, I guess, in the other direction, but that gives me a delta of 18. So if I just say that since it's, my equation becomes, let me slide down a little bit, I have zeta equals to 1 over 50, or 50 is my omega n, times 18 over 0.7, and the negative signs cancel out, and I get a zeta equal to 0.51. Is that right? Yes, it is, 0.5. Okay. So that worked out pretty good. I can also look for my resonant frequency point, given that information, omega res, slide up, okay, omega, which is at the peak of this thing, which happens somewhere right in there, is equal to omega n times the square root of 1 minus 2 zeta squared, and that comes out to equal to 34. So this is 10, 20, 34 as a check, and that happens right there, and that is pretty close to the peak, so that's another quick double check that says I probably didn't get something off by an order of magnitude or so. So here we have another set of plots. In this case, I've set zeta equal to 0.2. We'll see how well we can recover that. Now I've got some good oscillations, so I can probably use the log decrement method and the other methods for finding the zeta from the oscillations. If we start with a step response, I've got my damped natural frequency, omega d, equals to 2 pi over Td, where Td is the damped oscillation frequency period. Okay. In this case, I have Td equals Td is equal to 0.321 here, minus this point up here where I'm at 0.064, and I'm going to divide that by 2 because that's over 2 cycles, and that's equal to 0.128 radians per second, okay? And given that, I come up with an omega damped equals to 49, and that's a little less than the 50, and that's because it's equal to omega n times the square root of 1 minus zeta squared. Running out of room on the edge there, okay? So we can check on omega n by finding zeta squared and solving this equation for omega n since we have omega d. So to find zeta, we can use the log decrement method. The log decrement method, we look at the delta in the amplitude. And essentially take the log of that. So my equation for that is delta equals 1 over n, where n is the number of periods, and in this case we're going over 2 periods, times the natural log of yi, which is my y at n equals to my first point here, n equals 1, minus yf. So yi minus yf is this quantity, and then divided by yi plus n, so that's this point here, yi plus n minus yf, and that my yi equals 1.53, yi plus n equals 1.04, where n equals 2. So in my yf equals 1. So if I plug all that in, I get delta equals 1/2 log of 1.53 minus 1 over 1.04 minus 1. And that delta equals 1.29. So given delta, and that's fairly small, I can use my small angle approximation for zeta, and the full one is in the, no, we'll do it. We'll do them both. So I say that my equation here is that zeta squared equals, zeta, excuse me, equals 8 over 8 delta over 2 pi equals 0.205, and that's pretty close to what we actually did. If I work out the whole expression for zeta, which I don't have written down here, which just basically says that well, if I work from, where's some room? I'll write it over here. Delta equals this quantity here, which is equal to 2 pi zeta all over square root of 1 minus zeta squared. So if I chug and I chug and I huff and I puff and I blow the house down, I come up with zeta squared equals delta squared all over 2 pi squared plus delta squared, and that in the end leaves me with the zeta equal 0.201. So it's not much different. When we get a lot of oscillations and overshoot like this, there really isn't much difference between the small angle or small zeta approximation and actually cranking it out. In the cases where we just had that overshoot in there we have to actually do all the math because zeta is big enough for it to make a difference. Okay. That was the log decrement method. Now we can do the overshoot method. Erase all this. Our overshoot equation is another one of these zeta over square root of 1 minus zeta squared, because basically we're looking at the ratio of the time response, and it just all works out like this, equals 1 over pi times the log of yf minus y0 over os, or overshoot. In this case, yf equals 1, y0 equals 0, our overshoot equals 0.53. If I assume that the square root of 1 minus zeta squared is pretty close to 1, then I can just say, I can erase this and say zeta is equal to that, and I come up with zeta equal 0.202. So there, that's that method again applied to the step response. Now we have techniques for the looking at the Bode plot. Our amplitude method slides down. Now remember, basically the magnitude of g, j, omega n, the amplitude of the transfer function at omega n, divided by the amplitude of g, j0, the amplitude of the transfer function at a frequency equal to 0, comes out to be 1 over 2 zeta, because when you put all those numbers, put those two equations one on top of the other, and you start substituting in omega n's and zeros, you get a lot of ones, and you get a lot of zeros, and most of the terms fall out, and all you're left is this 1 over 2 zeta. So that's that equation. We need omega n. Now, for a second order system, that's right where the phase crosses minus 90, okay, and right there, which is at 50. And when I zoom that up to my plot up here for the magnitude, it doesn't quite hit the peak, right? It's the resonant frequency is to the left of the peak, so I can't just look at the peak frequency. And here I've blown it up. So I have to look at the magnitude at this point for my, to plug into here. And that's at right across 50, or 10 to the 1.7 is 50. I checked. So my magnitude here is, okay, so my magnitude is 7.8 dB at omega equals 50, where I believe omega n is. Now that's the magnitude in dB. I need the actual magnitude. So I need equals 10 to the 7.8 over 20 to convert that in out of decibels, and I get 2.45. 2.45 equals 1 over 2 zeta from above. So zeta equals 1 over 2 times 2.45, and that equals to 0.203. So I have the zeta I need. I have omega n from where it crosses here. I have k because this, oops, up. I have k because this is at 0 dB. So I've got everything I need to fill out my my equation of the form, k omega n squared over s squared plus 2 zeta omega n plus omega n squared. I don't have to write that down. I've said it so many times. Okay, that's the amplitude method. That seemed to work. One more method here we can use is the half power. Our half power method says that if we look at our peak, in our magnitude plot, we have some peak magnitude here, and in our case here, if I look, if we look for our max, up here, and I come down 3 dB, that's half uppercase B. That's half power, and I look for omega 1, omega 2. I don't have to worry about omega n or anything. I'm just looking for those. And then I have my equation, zeta equals omega 2 minus omega 1 all over omega n. I guess I do have to worry about omega n there, but in terms of omega n, omega n is going to be somewhere over here in this thing. So let's plug in some numbers and see what we get. Carefully observing my picture here, I get my peak, J omega peak, equal to 8.14. If I come down 3 dB, I end up with about 0.5 dB, or about 5 dB, not 0.5. So I'm looking for the 5 dB points here, and then I look for omega 1 and omega 2 and omega 1 there, and those are happening at about this is about 10 to the 1.76. That's equal to 56.2, and this one here happens at 10 to the 1.65, near as I can get from the picture there, and that's equal to 44.7. If I plug them into my equation, zeta equals my delta, which is the 56.2 minus 44.7 over 2 omega n. Delta equals 56.2 minus 44.7. I get 0.11, which is not very close, but I didn't have very accurate numbers there. So I think, I don't know how long this has taken. It's taken entirely too long. I'm going to knock it off there. That should be just basically stepping through these techniques on systems overdamped, underdamped. You see, some cases one technique works and another won't, just because you don't, like here we don't have the overshoot. So thanks for watching.